Next, we're going to talk about the existence of Laplace transforms. Okay, so for the existence of Laplace transforms, what we're going to do is I want to figure out when do the Laplace transforms exist. So existence of Laplace transforms. And it turns out that our function, our Laplace transform exists given some mild conditions. So if you think about the Laplace transform of some function f, right, this is the integral from 0 to infinity, e to the negative st, f of t, dt. It turns out that this exists for some function f so long as f is continuous. Okay, so as long as f is continuous on the interval over which we're integrating, so from 0 to infinity, including 0, and we need f not to grow too fast. If f grows really, really fast, this is going to go to infinity. So we need f to be what's called exponentially bounded. So if f is exponentially bounded. Okay, so what that means is that there exists constants c and m such that f in absolute value is less than or equal to m, c e to the mt. And we want this to be true for all t in this interval from 0 to infinity. So for all t greater than or equal to 0. Okay, so that's an existence theorem. Again, not terribly important for what we're going to do right now, but when you start to use these Laplace transforms, it's helpful to know when you expect the Laplace transform to exist and when not. Okay, one other theorem, just while we're in this area, is the Riemann-Lebesgue lemma. So this is called the Riemann-Lebesgue lemma. Riemann is a name that's probably familiar to most of you because he did lots and lots of things. But he's probably most familiar to most of you for us having working with the Riemann integral, right? So this is the integral that he kind of pioneered. The Riemann integral had lots of problems with it though, so that if you have a function that's not too nice, really all the functions that you'd work with in calculus are nice, continuous, usually differentiable, so smooth functions like exponentials and cosines and square roots and all the usual nice functions that you have, natural log. But if your function's not that nice, then sometimes that integral might not exist. And so there's a kind of more robust version of integrating that was discovered by Henry Lebesgue. So for his dissertation, he fixed the Riemann integral, which is a heck of a dissertation. So anyways, so Riemann and Lebesgue are the two big names as far as integration goes. And they have what's called a Riemann-Lebesgue lemma. So this is not something that they did together, but something that their work together, if you kind of pool their collective works together, one of the things that comes out is the following. And again, the Riemann-Lebesgue lemma is actually a statement about the Fourier transform, but since the Laplace transform is a special case, this also says something about the Laplace transform. So it turns out that if capital F is the Laplace transform of some function, okay, so remember that we're following our same convention that little f is our input function, capital F is our output. So if capital F exists, then it has to be the case that as s goes to infinity, capital F of s must go to 0. So this is a consequence of the Riemann-Lebesgue lemma. So what that means is that you can never have a function, there is no function f where the Laplace transform of f is, say, s, right? This can't happen. Okay, so this can't happen for any f, okay? Right, for any for any function f. There is no function f with this property. Because if there was, that would violate the Riemann-Lebesgue lemma, because s doesn't go to 0 as s goes to infinity, right? It goes to infinity. So anyways, this is the Riemann-Lebesgue lemma. So what we're going to do next in the next video is talk about inverse Laplace transforms, and then we'll be ready to apply this to differential equations.